Good afternoon, everyone, and welcome to another great webinar. This is presented by the New England Regional Defense Industry Collaboration, NERDIC. Those of you who have participated before, thank you for coming back on again. And for the new folks here, you're going to hear a little bit more about NERDIC in just a moment, but a great regional defense collaboration. Today, we're talking about machine tool probing for Industry 4.0, a really vital use of technology, automation, time savings, cost savings. You're going to hear a lot about this, so it's going to be a great presentation. As always, we have a really full agenda. We take up the full time here, but I'm going to give some brief remarks. Tina Chasm from New Hampshire, Department of Business and Economic Affairs is going to come on. We're going to talk a bit about NERDIC. And you're going to have Justin Lebel. He's a sales application engineer with Renishaw, who's actually going to be giving the technical overview today. And then, of course, we have some great demonstration pilots and programs, things to offer the supply chain companies. And Nasir, Mannan, our principal engineer at CCAT, is going to be giving that overview. So as we get into NERDIC, this is a nice little slide depicting the ecosystem that NERDIC is representing. So again, New England Regional Defense Industry Collaboration. This is something you don't hear about very often. We all are very uniquely focused on our states and the different challenges in the supply chain. But, you know, our states are so tied together, whether it's our industry partners who have facilities in different states, certainly when it comes to transportation, logistics, supply chain. So NERDIC is just a phenomenal resource for all of us to continue to buy into and build a sustainable platform. There's a great steering committee. A great consultant, Future IQ, is on board here leading this way. We want NERDIC to continue to grow and be a major part of our manufacturing ecosystem throughout New England. We want to make sure that we're all doing things to really increase the capabilities in a workforce that we're all going to need going forward. So NERDIC just uniquely addresses whether it's the supply chain, you got industry at the table, you have the MEPs at the table, you've got the PTAPs, the Procurement Technical Assistance Programs at the table, you've got educational institutions at the table. You really have all these great things. And as you look at the slide to the right side there, all the different things that we're addressing, from model-based definition, advanced design, augmented reality, a big part of what we're looking at here, certainly automation, cloud computing, and it gets right down to some of the very key things also that the MEPs are focused in. So you got things like cybersecurity, another very important initiative that's being directed through NERDIC. And again, that's going to be something we're looking at a holistic way all throughout New England. So look at NERDIC a lot more, become more familiar with it, stay active with it, because we really want to continue to grow this platform out and make this a great regional collaboration for all of us. So on that note, I'd like to bring on Tina Chasm. I think Tina's having a little difficulty with her video, so we'll be hearing from her today. But Tina, if you've got your audio on, we'd love to hear some remarks from you about New Hampshire and what's going on and your experience with the MEPs and NERDIC and even the program today.
Thanks so much, Ron, and thank you everybody for making the time to be here today. And I apologize for my technical glitches and not being able to get on camera. I certainly appreciate everybody's time getting on here today, but we've got some really great resources and great information to be shared. You know, this collaboration has been a few years in the making, and so we're excited to actually get some work off of the ground. And I can't say enough about the great things that CCAT has done, as well as all of the MEPs across the state and my colleagues from across the region. You know, we all see the value in this. We all see the importance of being able to work together across borders and to be able to share ideas, because certainly there's probably a wonderful, great idea located up in Maine that someone down in Connecticut can actually, you know, help formulate and bring forward into a product or a service. So that's the point of all of this, is to be able to work together and to become and remain competitive and innovative. And you know, if this is the first time that you've been on this webinar, on this series of webinars, please come back. There's a really good lineup going through this summer. And for And again, also you can check out the webinars that have already taken place. A lot of really great information. The defense industry is incredibly important to our region, and we certainly want to do everything that we can to help us be competitive, not just domestically, but globally, and bring all the benefits to the region. So I'm really excited that you're here. All our state partners are excited to be able to bring forward any resources that we're able to help you as the manufacturers move forward and get to where you want to be as industry. So thank you again for your time, and hope to see you all soon in person. Ron, back to you.
Yeah, Tina, thank you. And as you can see on the slide, you've got these 6 MEPs listed below. The manufacturing extension programs are so vitally important. They are really kind of that boots on the ground, really understanding that supply chain and that manufacturing ecosystem within each state. To have them pulled together like this, Tina, you must get a lot of satisfaction seeing all of them come together. And as you said, you folks have been doing this in the making for a couple of years. So finally seeing the kind of programming and all of us coming together has got to be something that you feel good about. And do you see this as we continue on? What other initiatives that you think are going to be really important that you're hearing from the manufacturers in your state that probably have a lot to do with other states as well?
Yeah, I think if we've learned anything over the past year and a half, it's being able to diversify and to pivot quickly and to be open to new opportunities. We've all faced the challenges of supply chains, both domestically and internationally. So how do we try to mitigate some of those risks? How can we set up our manufacturing so that we are nimble and able to pivot depending on the need or the circumstances that come down the pike? But I think also looking forward and taking that next step in our industry, in the defense industry and manufacturing, and being able to think a few steps ahead of where we are right now. That is going to be key. There's a lot that we can do here in the region. We've got incredible talent, we've got incredible resources, but it's being able to be open to looking forward. And I think that's one of the key things. Talking about Industry 4.0, talking about readiness, being able to jump on opportunities when they come forward. How can we turn around to be able to help you guys achieve that?
Yeah, Tina, those are just so great things. I mean, staying on that leading edge, and certainly on the technology side, but the technical capabilities of our supply chain, and making sure that we've got the workforce that's being upskilled or the future workforce being trained right now to take full advantage of those capabilities. So yeah, you're right on there. We need to be looking outward, and I think the other thing you talked about with the pandemic is just being able to adapt, being flexible, and that's been very, very important to our industry over the years. Even now, again, you mentioned supply chain. You look at going from a half a submarine some years ago to 1 submarine. Now we're going to be going to 2 subs, and so much of that is sourced throughout New England. And how do you continue to build up the capacity in that industry? So everything around our defense industry is growing. How we learn from best practices, how we leverage each other's resources is going to be vital to this area. I mean, this region, if we're connected the right way, can compete with any other place around the world. These 6 states that we've got here. So the more we can do together and collaborate, the better. So Tina, thank you very much for coming on, and looking for a lot more great things coming out of the MEPs and everyone's participation going forward. So thank you.
Thank you, Ron. Thank you, everyone.
So now for the main part of our program, I just want to say a couple things. The handouts for this part of the program are going to be available online. I think they're going to be sent to you as well. There are going to be some fantastic information on there. Also, if you have any questions, you can go right into the chat room, put a question in, and they'll be addressed after. So Justin Lebel, Justin, you're going to come on now. Justin's a sales applications engineer with Renishaw, and Justin, you got a heck of a program. I've got a little preview of it, so I got to thumb through it. But you know, you're going to really show us how technology, in this case, what we're doing on machine probing, what it can be doing for technology and certainly cost savings and time savings, and you know, all the inspection that Renishaw is doing. You guys are just a leading technology provider around the world, and it's great having you on. So we'll turn the program over to you now.
All right, thank you very much, Ron. Yeah, absolutely. Hope everyone today gets at least something out of this. We're going to talk about some of the benefits of probing. I'm going to hop off camera here so we get a nice full picture of what I'm showing. But as we move forward here, today, as mentioned, we're going to be discussing machine tool probing with its relationship to Industry 4.0. So my name is Justin Lebel. I'm a sales applications engineer for Renishaw. I cover the Northeast US, mainly the New England states, but also the Mid-Atlantic. I specialize in the calibration and machine tool product lines that we offer, and my main purpose is serving our customers here with pre-sales and post-sales technical support. So to start off, we have to take a look at the design principles for Industry 4.0. There's 4 design principles, and they support companies in identifying and implementing Industry 4.0 scenarios. So there's interconnection, and that's the ability of machines, devices, sensors, and people to connect and communicate with each other via the Internet of Things or the Internet of People. You've got information transparency. So the transparency afforded by Industry 4.0 technology provides operators with vast amounts of useful information needed to make appropriate decisions. Interconnectivity allows operators to collect immense amounts of data and information from all points in the manufacturing process, and that aids in functionality and identifying key areas that can benefit from innovation and improvement. You have technical assistance. So first is the ability of the assistance systems to support humans by aggregating and visualizing information comprehensively for making informed decisions and solving urgent problems on short notice. Second is the ability of cyber-physical systems to physically support humans by conducting a range of tasks that are unpleasant, too exhausting, or unsafe for their human coworkers. We have decentralized decisions as the 4th principle, and that's the ability of cyber-physical systems to make decisions on their own and to perform their tasks as autonomously as possible. So only in cases of exceptions, interferences, or conflicting goals are tasks delegated to a higher level. Industry 4.0 envisions environmentally sustainable manufacturing by having green manufacturing processes, green supply chain management, and green products. So in this presentation here, it's going to consist of 3 major sections. So we're going to take a look at an introduction to some hardware and software that will explain the various probing hardware systems available from Renishaw, as well as the accompanying software options. The discussion is going to move on to the benefits of on-machine probing, touching on several key points that users of probing can't live without. And finally, the implementation of on-machine probing will be discussed, and we'll learn just how easy it is to start reaping the rewards of this versatile machine tool add-on. So if we take a look here at a probe, we're going to ask the question, what is a probe? Okay. So in essence, a probe is a highly repeatable switch. So similar to a light switch, a probe can be considered as either off or on, or in probe terminology, it's seated or triggered. Attaching a probe to a machine tool spindle creates what we would call a part probe, which can be used to make contact with the workpiece to set work offsets and measure features. Attaching a probe to the machine table or other part of the structure allows it to be used as a tool setter, and that allows lengths and diameters of tools to be measured live while in the machine. Probes can be either kinematic resistive types, as seen in this video here, or they can be a strain gauge type, which we'll actually touch on that a little bit later. So when you take a look at the probe here, there are several uses for machine tool probes, including part and fixture setup. You get tool setup as well. In-process inspection, which is measuring features of a workpiece as they are cut. Detection of broken tools during machine operation. And final inspection of the workpieces. Probes can also be used for things like machine geometry checks, inspecting for thermal growth of machine axes or misalignment of rotary axes. All of that functionality can lead to lights out manufacturing and unattended operation. The spindle probe systems come in two transmission types. We have optical or radio. Optical probes require a line of sight between the probe and the receiver unit, and they're generally better fit on smaller volume machines with no obstructions. Radio probes do not require a line of sight to the receiver, instead use a radio signal to transmit the data. So radio probes are typically used on larger frame machines or where multiple probes are being used on the same machine. Our systems offer up to 4 probes with a single receiver. So both transmission types are offered in the kinematic resistive probes, as we mentioned on the last slide, or strain gauge technology. Play the video here. So the kinematic resistive probes sense an increase in electrical resistance inside of the kinematic seat. That increases the resistance, the increase in resistance causes the circuit inside the probe to detect when the stylus has deflected. Kinematic probes are well suited for 2D probing. You get generally about a 1 micron repeatability. Strain gauge probes use a strain gauge arrangement in the kinematic seat to detect the stylus deflection at an even smaller level than the standard kinematic resistive probes. So that makes the strain gauge probes the optimal choice for tight tolerance or 3-dimensional applications. Repeatability of those probes is generally in the 0.25 micron range. For those counting along in inch, the 1 micron is about 40 millionths of an inch, and the quarter micron is about 10 millionths of an inch. In looking at the software, spindle probe, all of our spindle probe hardware has an array of software options available. So core probe programming typically comes from Inspection Plus, which is the macro-based software package. Inspection Plus now has the Super Touch optimization capability. That's designed to tune the probing feed rate to maximize your cycle time while maintaining the repeatability of the probe measurements. The optimization is run as a routine before you calibrate, and all cycles will run at the optimized feed rates. We have many cases in which the optimization has shown cycle time improvements of greater than 50%. So for anyone concerned about adding probing to the machines and it consuming too much cycle time, there are ways to greatly speed up the process without actually adding much to the total cycle. So GoProbe software builds on the functionality of the Inspection Plus, and that's implemented by an easy-to-use phone-based app with simple macro crawls. So a user can use the app to conversationally define the cycle that they wish to run, and the app returns the correct G-code callout to enter in the machine control to execute the probing cycle. GoProbe makes job setup quick and easy, as well as single cycle operations. Moving up the ladder there, we have Set and Inspect. That brings the functionality of GoProbe directly to the machine control or to a PC-based experience. The easy-to-use GUI creates single or multi-step cycles via conversational programming, sending the information directly to the machine in either an MDI or program format. The data that you collect with these cycles can then actually be sent back from the machine to the reporter application for process control information. Finally, at the top of the software ladder, you've got Productivity Plus and CAPS NC. Those are full CAD-based probe programming options. So Productivity Plus can be run independently or as an add-in to Mastercam CAM software. Both options allow easy integration of probe routines and logic into your machine cutting programs. CAPS NC offers a full GD&T analysis package, which gives your machine tool the functionality of a CMM. Another software is NC Perfect Part from MSP. That offers the ability to measure parts on the machine and then make live toolpath corrections to rework or to take final pass cuts. So we go from very, very basic, just G-code macro programming all the way up through full CAD-based and GD&T applications. The Set and Inspect, as I mentioned, this is an image that you would typically see from the GUI. So these are used to call single cycles very quickly at the machine tool control. You've got basic functionality like bores and bosses, pockets and webs. internal and external corners, lines, planes, rectangles, and we also have the ability to do rotary axis updates. So if you're measuring whether or not your part is aligned correctly on, say, a C-axis, you can probe a few points on the part and have the machine automatically set your 0 point. Moving on to our tool setting hardware. We have non-contact and contact sensing systems. So similar to the spindle probes, the tool setters include optical, radio, and also hardwired transmission capability. Contact systems use the kinematic mechanisms, while non-contact systems are laser-based. So the video that you're watching here shows how a tool comes into contact with the tool setting styli. This deflects the stylus, and that causes the kinematic seat to move. So the motion causes an increase in resistance in the electrical circuit, and that causes the probe to trigger and detect the length or the diameter of the tool, depending on the cycle you're running. Tool offsets are automatically uploaded to the machine tool control, and machining can then continue. Taking a look at the non-contact tool system. These options, again, are laser-based. So we have a connectorized version of the NC4. Oops. There we go. We have a connectorized version of the NC4. The options include the NC4, NC4 Plus for enhanced accuracy and repeatability, and the new NC4 Plus Blue, which uses a blue laser with a smaller wavelength, and that makes the system extremely accurate, gives the capability to measure tools down to 30 microns in diameter. So the non-contact systems will measure length and diameter by breaking the laser beam that causes a trigger signal in the machine tool control. The non-contact systems are also capable of detecting wear on your tools, thermal growth, and also broken tools. So when we look at our tool setting software, that includes software options for contact and non-contact cycles. The options for these packages include tool breakage detection with your optional redundant tool call or alarm generation, and automatic tool setting sequences. So tool setting programming is also made easy with the GoProbe application, just like you would use with your spindle probes. So now let's take a look at some of the benefits. We have an understanding now of what machine tool probing options are available. So let's take a look at why machine tool probing is so beneficial to your manufacturing operation. So things like scrap reduction, automation, increasing your productivity, inspection, and quality control all contribute to how fast you can see a return on investment for your machine tool probing system. So scrap reduction is a big one. If we take a look at scrap reduction, it can be one of the first things achievable with on-machine probing. So reducing scrap saves money not only in the form of materials and time or your labor cost, but increases your product yield, reduces your carbon footprint of the manufacturing operation, and reduces wear and tear on the machine. So if we take a look at an example here with a cycle time of 6 minutes, so you might get an argument that says adding a probe to the machine will increase your cycle time, as the machine now has to spend some time probing the part instead of making chips. So if a part cycle time is 6 minutes and you add 30 seconds of probing time, you've increased the cycle time by about 8%. If the process was producing 10 parts per hour, but 2 of those parts had defects and needed rework or were otherwise scrap, the true cycle time is no longer 6 minutes. It was actually 7.5 minutes per good part that you're producing. So to produce 10 good parts at this rate is actually 75 minutes. By adding 30 seconds of probing per part, your total cycle is 65 minutes for 10 good parts, because you're now catching any defects before they become scrap. So in compared to the 75 minutes for 10 good parts versus 65 minutes, that's actually a 14% reduction in cycle time for good parts. So knowing that, using that example, we've also increased the yield. So we're wasting less material in the process. Less material wasted means less material transported to the scrap dealer to be reprocessed, and less cost in the initial material purchase and recycling fees. It also means that there's less machine power was used to create a total number of parts, as every minute of the machine use was valuable machine use and not wasted effort. So you're saving electricity in that standpoint. This valuable machine use also means that there's less wear and tear on the machine, as every motion of the ball screw, the bearings, the spindle, and the tooling was used to create good parts. This also means that every minute an operator attended that machine was valuable use of that operator's time. Whether it was for setup, operation, or breakdown of the job, it was all value-added time. All of this, of course, relates to saving time and money. So probing leads to increased productivity. Machine tools can run at increased rates as less manual intervention is required. A probe in the machine is like having an operator with an edge finder, a micrometer, caliper, or dial indicator standing at the ready inside of the machine at all times, but the machine does not need to stop to let the operator open the door. Unattended operation is key to increasing your productivity without increasing your overhead. So an extra run can be loaded into the machine at the end of the day, and lights out manufacturing can be performed on overnight shifts so that a batch of parts is ready to unload as soon as crews arrive in the morning. Machines are smart, but they can only do what they're told. So probing allows machines to make decisions on their own about the best way to handle certain situations. Your productivity will increase when you let your assets work for you. The return on investment for a probing system is often measured in days or weeks, not months or years. Simple programming and training options allow your users to come up to speed very quickly on probe use. Initial hardware and installation investments can represent 5% of the initial machine cost on lower cost commodity type machine tools, but significantly less on high-end machines. The probe systems are relatively maintenance-free, requiring only occasional cleaning. Systems are designed to live in the machine tool. Spindle probes require battery changes, but battery life is significant and warning is given when it is time to change. So Renishaw also has a repair by exchange program known as RBE, and that allows for next day replacement of probing systems should a crash occur. Standard styli are also stocked as well. Inspecting critical features in the machine can save dozens of hours in removing the part from the machine to inspect it on a CMM, only to find that the component needs reworking and then must now be refixtured, relocated, and machined again. Parts can be inspected in process to see that critical features meet tolerances before they leave the machine for the next operation. If the machine is calibrated and qualified for part measurement, final inspection can also be done on the machining center. Software options allow for full reporting of feature size and position, from basic software packages all the way up to that full GD&T quality reports on the more advanced software packages. So finally, automation is every manufacturer's dream, as long as the automation creates more benefit than problems. One huge benefit to automating a manufacturing operation is the removal of operator error. As humans, we are fallible and we all make mistakes, but some mistakes can be costlier than others. A transposition of two numbers or a decimal point may seem insignificant, but when an end mill is 6.0 inches long and not 0.6 inches long, the consequence, especially on a high dollar component, can be catastrophic, not only to the part, but to the machine and possibly the operator. So using tool setting to automate the offset definitions removes any possibility of human error, as does using a probe to locate the part in the machine volume. Anytime a machine has to be entered by the operator, there is a danger for injury. So if we pretend the door on the machine is locked and an offset needs to be set, what's the best way to perform this? Typically with a probing system. Automating the work setup and tool setup creates a safer working condition. The intermediate steps so common in traditional manufacturing, things like cut, measure, cut, measure, cut, measure, can be reduced to simply cut once, probe, and take your final cut. So in the event of a tool breakage, logic can be initiated to call redundant tooling. In operations where tombstones or multiple fixtures are used, the tool can be checked after each part. If a tool is found to be broken, that part can be flagged as potentially damaged, but the operation does not need to stop. A sister tool can be called from the carousel and the operation can continue, finishing the batch with minimal interruption. Using multiple fixture setup as an example, we can see how probing can get the job done quickly and accurately. So there are two approaches to fixture setup in the case where multiple stations are involved. The first would be to locate the first station and then assume that the other stations are in their designed location relative to the first station. This assumption requires two things to be correct. The first being that the fixture itself is manufactured to the exact specifications, and the second is that the machine is positioning to the correct location. If either assumption is incorrect, then the parts made in the subsequent locations can be off in size or position. The second approach to fixture setup for multiple stations is to locate each part or station individually using a work offset. Traditionally, this would be the most accurate way, but can take more time as edge finding and indicating would be required at each station. So a simple 4-station fixture might be manageable, but what happens if the fixture is a tombstone with 4 sides and 4 stations per side? Now that's going to take some time to perform that setup. So in the previously mentioned example, we had a customer who experienced just that problem. They had a 4-sided tombstone with 3 stations per side that was being used to manufacture some components, but the parts were not only being machined on the front of the tombstone, but also being machined from the sides or the ends of the parts. So it essentially created the need to have 9 separate work offsets per side of the tombstone. It was done as the fixturing and the machine combination was not perfect, because it usually never is, and locating all the parts was the most accurate way to machine them. The problem was that this setup operation generally took about 4 hours for an operator to perform. So we introduced a machine tool spindle probe. The parts were loaded and the program was started, and the probe takes care of the rest. So each part was located on the fixture for each orientation of the B-axis table, automatically as part of the cutting program. The result was an increase in the machining cycle time of approximately 45 minutes because we added all the probing at the beginning, but an overall decrease in the setup time of 3 hours and 15 minutes. So it not only reduced the overall time to complete the job, but it freed up the operator to move on to setting up another machine while the first one started running parts. So implementing machine tool probing on most machines is a straightforward process. Hardware and software packages for a variety of control types are readily available, with most installations and training sessions taking 1 to 3 days depending on the complexity. The phone-based, control-based, and PC-based applications make programming simple and accessible for everyone from machine operators and setup personnel all the way to CAD and CAM programmers and quality control planners. The reporting functionality for data output allows the data to be collected in various software packages for process control. So in recapping our machine tool probing and its relationship to Industry 4.0, we find that the interconnection of machinery and people is supported by the machine tool applications such as Reporter, which can report live data from the machine tool as parts are being measured. This can be collected in Renishaw Central software at a single location to view your entire factory data stream. Information transparency is afforded real time by the measurements taken by the probes. So you can find out, is the process in control? Is it losing control? Actions then can be proactive during the process instead of reactive after the process is finished. Technical assistance is gained by letting the probes measure work offsets, tool offsets, and features automatically in the machine. This makes the process faster with less intervention by operators and makes the operation safer. And then decentralized decisions occur with logic written directly into the CNC cutting program. Probes can inspect your parts and tooling to ensure the sizes are met or broken and damaged tools are flagged. Logic statements can help the process continue on its own or alert an operator to an anomaly. This moves the bulk of the decision-making to the machine, driven by data. So these achievements ultimately help create more sustainable manufacturing with reduced waste, increased throughput, and valuable resource usage. So machine tool probing falls into Renishaw's productive process pyramid. This methodology is what Renishaw uses in our own manufacturing to help streamline efficiency, reduce scrap, improve quality, and utilize automation to maximize the use of equipment and manpower. The pyramid consists of 4 levels, starting with the process foundation, moving up to process setting, then in-process control, followed by post-process monitoring. The levels relate to preventative, predictive, active, and informative controls and what can be done at each level of the manufacturing process. Machine tool probing generally fits into the 2nd and 3rd levels of the pyramid, involving process setting and in-process control. So this video here demonstrates the various integrated process control solutions available from Renishaw. Not only do we promote this equipment, but we use all of our own products within our own manufacturing facilities on a daily basis. We have created highly automated manufacturing processes that allow maximum throughput, minimal downtime, and delivery of the highest quality manufactured components possible. Renishaw has been employing Industry 4.0 principles for almost 25 years before the term Industry 4.0 was coined. Following our productive process pyramid, we apply preventative controls in advance of cutting operations. This includes ball bar testing and laser calibration of our machine tools, as well as reference artifact probing. This helps ensure parts are accurate the first time. We move on to predictive controls, which are applied just before production starts. Predictive controls help to eliminate errors in the setup by automatically updating work and tool offsets and correct for machine dynamics. Predictive controls also help to minimize part setup time and part-to-part setup variability. Active controls are then applied during the metal cutting process. Active controls help ensure accurate machining and can be used to measure features in process. This allows for correction of tool wear and can stop operations or call redundant tooling in the event of tool breakage. Internal and external gauging systems allow for process control data to be collected and automatically keep the process within specified control limits. Informative controls are finally applied after machining is complete. Informative controls allow for accreditation of the operations and sign off of parts as they meet the design requirements. So this framework has been developed from our decades of experience as a manufacturer. Renishaw has lived and breathed process control for decades, and through a hard-earned experience, we want to help you make the most of your manufacturing processes. When you stop fighting fires and solving small problems on a daily basis, you can step back and look at the big picture and explore the power of process control to maximize your efficiency. So Renishaw was founded in the UK by Sir David McMurtry. While an engineer at Rolls-Royce, David McMurtry designed and built what would become the first touch trigger CMM probe to solve a measurement problem on the Olympus engines for Concorde. So fast forward almost 50 years, and Renishaw has become a world leader in metrology systems for solving the diverse needs of manufacturers in every industry, from medical, aerospace, transportation, energy, and electronics manufacturers, to name a few. Renishaw was founded on innovation and continues to do so by investing heavily in research and development to stay on the cutting edge of technology. With close to 4,500 employees worldwide and over 500 million pounds in revenue yearly, we continue to grow to serve our diverse range of customers the world over. And I believe that is the end of my presentation. So we'll open it up for the Q&A now, and I believe Nasir is going to join us.
Yeah, thank you, Justin, for that wonderful presentation on Renishaw's technology. This is really it's really great how this technology can improve manufacturing processes by giving that feedback while the part is in production. If you want to go to the next slide. Okay, so we do have, I wanted to bring to your attention that we do have a number of opportunities for defense supplier companies to participate on technology demonstrations. We welcome you to apply for these no-cost technology projects by going to CCAT.us /NERDIC /apply. We'll also be sending this link to you following this presentation. But companies that have more than 5% sales in the last 5 years for defense-related components are welcome to apply. Next slide, please. We are seeking more pilot applications for the additive manufacturing pilots for projects to be demonstrated in August with our technology partners at the Berkshire Innovation Center, University of Maine, Center for Advanced Manufacturing of Metals, and Vermont Technical College and CCAT. Companies that are exploring additive manufacturing would like to be introduced to the benefits of additive manufacturing are invited to submit an application for a no-cost technology demonstration. Some of the applications that additive manufacturing affords include lightweighting, assembly consolidation, and geometry optimization. So parts that fit within like an 8-inch cube volume that have long lead times or are expensive to produce would be prime candidates. We have extended the date to apply for the technology demonstration to June 30th. We have a number of technology demonstrations coming up over the next 2 months. On June 22nd, 12 to 1, I'd welcome you to tune in to see a detailed demonstration of creating a model-based definition file and really what's involved. On July 13th, 12 to 1, we will be presenting a case study using machine tool probing on CCAT's Mazak machine. On July 20th, 12 to 1, Stanley X will present the results of the technology projects underway currently using their AI-driven DeepHow platform. On July 27th, 12 to 1, SphereGen will present the results of the augmented and mixed reality pilot projects underway with 2 companies. And on August 10th, 17th, and 31st from 12 to 1:30, the results of the additive manufacturing projects will be presented by our technology partners, as I mentioned, at the BIC, University of Maine and Vermont Technical College. The presentations on all these technology demonstration projects are really meant to illustrate real-world applications of these technologies. What challenges in manufacturing processes these technologies help to address, and how the technology was applied between the different pilot projects, and what the outcome was. So we welcome you to register to attend these presentations at ccat.us/NERDIC. With that, I'd like to thank you for your time today, and we would really appreciate your feedback on a survey. You'll get that right after the webinar ends. This really tells us, how beneficial this particular technology introduction was, what other technologies might be of interest to you to learn more about. And also, it'll give you a chance to also go to the website and sign up for technology demonstrations. If you have any additional questions, please do feel free to contact myself. My email's there listed at the bottom. And again, thank you. And we'd like to open it up now to questions. I'm looking at, if you look over to your right side of the GoToWebinar control panel, you'll see an area questions drop down. You can feel free to add your questions in there, and I'll read them out one by one for Justin to answer. So I do see a few in there right now. Justin, one of the questions here is, how widespread is the use of machine tool probing?
It's surprisingly not as common as as we would like anyway. But there's, I would say on average, you're probably looking at 30 to 40% of machine tools sold are equipped with probing. So obviously there's a huge capability gap that exists in the market. The nice part about machine tool probing is that it's not just limited to brand new machines that are sold. You don't have to get it installed from the factory. We can install probes on machines. Really, the limit is the control that's on the machine. Typically, we can go all the way back to like FANUC 15. So machines that are like 25, 30 years old can be fitted with probes and use that technology to increase that productivity, even on older equipment. So I would encourage anyone who's thinking about it to reach out to us and have a conversation, because again, it's not just limited to brand new machines. It applies to just about any CNC control out there. So.
Another question that's here is, are there a lot of companies that use on-machine probing?
Yeah, so typically what happens is companies that get probing, they start with a few machines with the probing, and they realize the benefits very quickly. So then they start to reach out and want to start applying probing to all of the equipment that they have. So as far as the number of companies out there using probing, it's hard to say, but typically companies that use probing use it across the board. There's very few instances in which a company has a single machine with a single probe on it, and that's what they're happy with. Most of the time they adopt this technology to benefit all the machines in their shop.
So another question here, following a comment, is very interesting that you mentioned machine tool probing can provide CMM capability. This would seem like a very cost-effective way to get CMM capability. Is this true?
Yeah, so the big caveat obviously is that the machine has to be qualified the same way a CMM is qualified and certified to be accurate when measuring the part. Machine tool has to go through that same process, but if the machine has been qualified, you can certainly use it to measure the part. Now, if you're producing 1,000 parts a day, you probably don't want to be measuring every feature of every part on the machine, because that's consuming valuable machining time. So you'll want to offload that off the machine to some other gauge or CMM. But high dollar or really expensive components that take a long time to machine, it's more costly to pull them off the machine to find out you have to rework them and then figure out how to fixture them again and make sure you're in the exact same spot you were and relocate it. So if you can find the condition of the part before it comes off the machine, that's just a huge time saver because you don't have to rework it after the fact, right? You don't have to pull it off and use your CMM time.
Is there any limitation on the types of machines that can do on-machine probing?
So we install probes on turning centers, milling centers, horizontal, vertical, 3-axis, 5-axis, pretty much any metal cutting machine we have a probe system for. Things like water jet, no, you know, it's not really, the accuracy is not quite needed there. But, you know, most metal cutting machinery, we can generally fit a probe system on.
Okay. And the qualification of the machine that you mentioned, that would be on the axis accuracy and the kind of the global accuracy that the system itself can move the probe in?
Yes, yeah. So when you qualify a CMM, typically you're measuring the axes for their accuracy, and you're creating an error map, which essentially makes the volume of the CMM a known accuracy. That's verified by using a certified length standard, like a gauge, a step gauge, and then measuring that gauge with the machine. So if you've ever mapped the machine, the CMM rather, and then you measure this known artifact, this known gauge, that gives you an idea that this machine is qualified. So same thing goes with your CNC machine. If you measure an artifact in the machine that you know is a true size, you've calibrated your machine to be as accurate as possible, and then inspect it with a probe, you're going to know what is the measurement capability of that machine tool.
I see. So it's not a compensation for that accuracy of the machine. It's more just mapping out.
Correct. Yeah. So you can obviously improve the accuracy of the machine with like laser compensation and things like that. But the true qualification of it is to do an artifact measurement on the machine. So have a certified gauge that you then probe using the machine tool. The results of that will tell you how qualified the machine is to make measurements. And if it's within your tolerances on your parts, then you've got a qualified CMM essentially as your machine tool.
I see. In terms of what would be some limitations for on machine probing? What would be some of the limiting applications?
Okay, so you can't, generally most of the probes cannot probe in the plus Z direction. So if you're trying to probe an undercut on a part, say, right, you can use a star stylus, right, to actually reach underneath, but the probes themselves mechanically won't measure like straight up in Z. So you have to have a fairly large offset with your star stylus so that it actually tilts and doesn't pull straight down. So that's one big limitation, is that it's typically plus X and Y and then minus Z. Those are the, the plus and minus X and Y rather, and minus Z for your probing directions. There are other limitations. We talked about optical versus radio. If you're on a large machine with an optical probe, you might lose the line of sight. If you can't talk to the probe, then we can't use it. Some machines, even smaller machines, depending on the part that you're making, if you have say a round part and you're going down inside of it with the probe, if you block the line of sight by going inside the part, you can't use the optical probe either. So in kind of trying to future-proof your applications or what you might end up doing down the road, that can kind of help you steer the direction as to which system you might be better off with. So there's limitations to how long the stylus can be. Generally, the longer it is, the heavier it's going to be. So you'll have a lot more over travel before we trigger. It can affect the accuracy a little bit, but you typically build the probe for the worst case application, if you will. And if it can do that, then you should be good with everything else.
Okay. What would be like a typical process for onboarding on machine probing? If I was a company that was interested in adopting this kind of technology, what's typically involved there?
So a typical, say, retrofit is having a representative from Renishaw come out to your facility for the installation. Our engineers will actually install the probe, so we wire the receiver to the machine, we commission the probe, we calibrate it for you, and then that includes generally 1 to 2 days of training as well. So if you're using the Inspection Plus or the GoProbe cycles, we'll walk you through how to use those. If you have a specific application that you're working on, we can also assist with getting you started on that. Yeah, generally the whole process is like a 1 to 3 day, depending on how quick the install goes and also how much training you require. When you move up in like software class, if you're doing like the CAD-based programming, those aren't necessarily tied to installs a lot of times. The installation, if you will, relates more to the commissioning of the post processor for the software to actually generate all of the code correctly for your machine tool. Much like a CAM provider would create a post processor for your machine, we do the same thing with our probing software so that the post spits out the correct code for you.
Okay. And some of the advanced features on some of your standalone CMMs, such as the scanning capability, is that available with the on-machine probing?
Yeah, so we do have some higher end probes. All the probes that I discussed in this webinar were touch probes, so they take a single point contact. We do have the OSP60, which is a scanning probe. So that takes 1,000 points a second in constant contact with the surface of the part. That's programmed exclusively through the Productivity Plus package. So you have a CAD model of the part that you're going to be scanning a specific path on. The part obviously can deviate from that. That's what you're trying to find. But you're limited obviously with how far it can deviate, just like you would on a CMM scanning application. So we do have the ability to do scanning on the machine tools as well. It's a bit more of an advanced hardware and software package, but for the right application, it can give very, very important information on the condition of the parts.
Okay, and does that come with that scanning capability come with any limitations on the type of machine? Is it limited to 5-axis only?
Nope, you can do 3-axis. It is generally for higher end controls. So like think FANUC 31i, Siemens 840D, Mazak Smooth controls, the higher level ones. So we do require, on some cases, a secondary data processing unit because of the amount of information that's coming across. Some of the machines can go right into the control. The control being a PC-based platform can handle that amount of information. Others are not, so you need to have a separate unit, but it is functional in those different applications. But typically that's again geared towards the more higher end machine tools or the newer controls.
Okay. Well, I continue to welcome the questions coming in. If you if you think of something, please do again reach out, and I can forward the question on to Justin to help answer any additional questions that you might have on this particular technology. I did want to mention just in closing that we do have an opportunity that I just wanted to bring to your attention about our the website that points to the small engines, what is it? The small turbine engine opportunity for the USAF, for the Air Force. This is an opportunity for defense supply companies to be put on the Air Force's list for a supplier list to produce parts for the small turbine engine. These are engines that produce less than about 2,000 pound-foot of torque thrust. If you're interested in it to learn more, I'd welcome you to go to sep.ccat.us, and we'll include this information as part of the package that we'll send to you. Just wanted to quickly mention that that is an opportunity for defense supply companies. And with that, I'd like to thank you again for your time, for tuning in. I really thank you, Justin, for that great presentation, and wanted to wish everybody a great rest of the day.
Okay, thanks for the opportunity. Appreciate it.
Yeah.
Thank you very much. Bye.